isn't that 4 on the one side and then 1 on the other?
We look at the change here, we just look at the stoichiometric change. This is 1 for 1 here, so we use the same number here.
Yeah.
This is, we're using 2 for every one. So if you take this and multiply by 2,
okay.
that's where it came from. We have all the numbers. Putting in the numbers, the value you get is about 9.43. And that is the Kc for that reaction. Looking at it, relative scale, greater than 1, still more product favored. Good.
I'm getting 0.05. I don't know how I'm getting that.
I will check your calculator when we.
Okay.
Yeah, I did it. I got the right answer.
9.43. Again, product favored, 9 to 1. Yeah, we still make a product off it. No doubt about that. All right. Let's look at the one last thing before we go to first break. So this is the one type of equilibrium problem that you'll see. The neat thing about it is that the logic will apply to the equilibrium problems that we see here will be the same we see in the next chapter. It'll just be a type of equilibrium we look at. So the way we solve it stays the same. We don't always just have to worry about equilibrium. There is another quantity. This is called the reaction quotient. Signified with a Q. And what a Q, what this tells you is, it talks about the ratio of products to reactants, but it talks about what the number could be, Q, when it's not at equilibrium. So basically, just like A, but not at equilibrium. We use this often because sometimes when we're looking at a reaction and we measure different values, we want to know, did we get to equilibrium yet? Did we slide past it and the reaction is going to reverse? Or are we right at equilibrium? When we look at this, just a quick comparison, if Q is less than the equilibrium constant K, Q is smaller than K, then the reaction still has to proceed forward. The reaction is going towards the product. That is, it's not done yet. The reaction's still happening, but it hasn't settled yet. You're seeing the reaction, you're seeing the concentration at some concentration prior to striking the balance, still getting to the equilibrium. Obviously, if you measure the value and the Q value you get is the same as K, then you made it. You're at equilibrium. If you measure your concentrations and you find that Q is greater than K, that means the reaction's actually gone beyond equilibrium. It's settled beyond where you think. And this will happen. Sometimes the reaction will go forward a little bit and then back up. This is essentially the reaction will move towards the reactants. It's got to back up a little bit. If you look at these three, if Q is less than K, it stops short of equilibrium. At the right point where they're saying that heat hit equilibrium, the other one, it stopped too far and has to back up to get to equilibrium. And reactions will do that. Temperature changes will swing equilibrium back and forth like a pendulum. We very much look at a pendulum as being the perfect point. You can go above and below that. That's what's happening. But we find it the same way. We look at Q numerically the same way. Let me show you 667, a quick problem that shows us equilibrium settle. Here they gave us a reaction says N2O4, 2NO2. Everything's a gas. It was measured, or has a KC of 5.85, 10 minus 30. So it has an equilibrium constant. It's very small, so it's kind of already looking at going backwards. And it asks you to find a reaction mixture contains NO2 equals 0.0255. So it gives us a set of conditions, and it asks us to find Q, find out what the numerical is. Find it the same way that you find equilibrium constant. Equilibrium constant says products. Our products are NO2, second power, over N2O4. We put in the numbers. NO2 is 1.0255. Let me just find out what the number's at. We're going to compare it, see how close it is. That Q value we'll get out of this, 1.96, 10 to the minus second. We compare it. This is where the reaction is right now, 1.96 to the minus second. This number, compared to where its equilibrium lies, if we look at that, that number, 1.96 to the minus second, is larger than the equilibrium constant. So if it's larger than the equilibrium constant, I'm saying that Q is greater than K. What has happened is the reaction is going beyond equilibrium. So the effect, they would say, is the reaction is beyond the equilibrium, and it will indeed move towards the reactants. It's going to shift back a little bit. It's past where it should be. It's going to back up a little bit until it gets the.
Just wondering why, never mind. Q, you square the top, and KC, you square the bottom.
What's that?
For Q, when you do the, you plug in the numbers, you square the top, and for KC, it's just you square the bottom.
No, the square here
Yeah.
is because that has a 2 in front of it.
Oh.
That goes with the, this had a 2 in front of it, so that has a, whatever the coefficients are in front, you have to, it goes with it.
Okay.
That shows it. Good.
We've been dealing with molarity this whole time.
This one here was given in molarity. They could, you'll see in the problems, they'll talk molarity, they'll talk atmospheres. You're going to treat them the same way.
Okay.
If they're by themselves, just treat them the same way. They're concentration units.
Okay.
Yeah, absolutely.
That's molarity.
Most likely you'll see, I think a lot of them start out, if they're all gas reactions, they'll flip back and forth. Sometimes they'll do an atmosphere, sometimes they'll do both. It doesn't matter, it's still the same numbers.
Okay.
Are you sure it's molarity? I thought it was molality because of the small m.
No,
Molarity
that's,
is the
that
one-
certainly is in moles per liter.
Oh.
Okay.
Gotcha.
All right. See you about 10 after.